Hello everyone. I am going to explain the topic of implementation of CRC for 5G. In this presentation, I would be highlighting the introduction, how this is beneficial, structure of the transport model, system model of the transport block and the code block, properties of CRC, CRC implementation by direct calculation, CRC implementation by parallel processing, CRC implementation by serial processing, the Sarvate algorithm, slicing by 4 and slicing by 8 algorithm, conclusions. Okay, so now starting with the introduction, over here in 5G, the medium access control layer organizes the data into transport layer and transmits it into the physical layer. Now here, the transport layer consists of million bits. So when the transport block exceeds a threshold, the transport block is divided into multiple equal sized code blocks. The code block consists of up to 8448 bits, and both the transport block and the code block have a cyclic redundancy attached. So due to this difference in the size of the transport block and the code block, the CRC processing scheme is suitable for the transport block and that suitable for the code block. Both are different. This is because of the difference in the size. Okay, so now how this CRC is beneficial over here. As there is a high data transmission rates, the bandwidth of mobile communication system is increasing. So in 4G, the maximum transmission bandwidth is 20 megahertz, and in 5G, the frequency bands are divided into two parts. That is the FR, which is below the 6 gigahertz, and FR2 above 24.25 gigahertz. So the maximum transmission bandwidth for one component is 100 megahertz and 400 megahertz in FR1 and FR2. So the increasing bandwidth brings problems to the design of transmitter and receiver. The CRC helps in the bandwidth adjustment. Okay, so the structure of the transport model over here, the MAC layer organizes the data into the transport layer and transmits it into the physical layer. So in 5G NR, the transport layer is 1,200,077 277 992. If the transport block size is larger than 3824, 16-bit CRC is added at the end of the transport block. Otherwise, 24 CRC is added at the end of the transport block. Over here by CRC, I mean cyclic redundancy codes. The transport block is divided into multiple size blocks. So when the transport block size exceeds the threshold, for QC LDPC1, the threshold is equal to 8448, and for QC LDPC2, the threshold is equal to 3840. In 5G NR, the maximum code block size number is 8448, and an additional 24 CRC is at the end of each code block when there is a segmentation. Okay, so now I'll be talking over about the system model of the transport block and the code block. Over here, let A be the transport block, L transport block size, N transport block level CRC size, and P over here is the transport block level CRC. And if L, that is the transport block size, is less than equals to 3824, then N is equals to 16. Then P is generated, that is the G16, G to the power 16x, which is the polynomial, is given by x to the power 16 plus x to the power 12 plus x to the power 5 plus 1. And if L is greater than 3824, the N over here, the transport block size equals to 24, then P is generated by the following. That is x to the power 24 plus x to the power 23 plus x to the power 18 plus x to the power 17 plus x to the power 14 plus x to the power 11 plus x to the power 10 plus x to the power 7 plus x to the power 6 plus x to the power 5 plus x to the power 4 plus x to the power 3 plus x plus 1. Basically, this was the polynomial expression. So if L plus N is greater than M, the transport block, including the transport block level CRC, segmented into multiple code blocks. Okay, so now coming further, R over here is the code rate of the initial transmission, which is indicated by the modulation and coding scheme. if here L is greater than 292 and R is greater than 0.67, or L is greater than 3824 and R is greater than 0.25, then M is 8448, else it is 3840. When there is no segmentation, the number of code blocks C is equals to 1, and when there is a segmentation, C equals to L plus N by M minus 24. So Ci be the ith code block, and then K is L plus N by C plus 24. This code word generates the polynomial. Okay, so here Cj to the power I equals to Ai K minus 24 plus J. So in the transmission, the transport code block includes QC, LPDC, encoding, rate matching, bit interleaving, and code block concatenation. Okay, so at the receiver side, the code block segmentation, bit de-interleaving, D-rate, matching, QC, uh, LPDC, decoding, code block concatenation. So we check the correctness of the code block received. So here DI is the ith received code block after hard decision, and E is the received transport block after the hard decision. So here the undetected error probability is required to be less than 10 to the power minus 6 in 5G, and since QC LDPC codes cannot alone meet the undetected error probability, so here we use the CRC to determine whether the D, I and E are correctly received. So coming to the properties of CRC, over here we can see that when CRC Gx, Ax into Bx, so it is given by the individual products. So over here we can say that Ax and Bx are computed independently. And when it is added, Ax plus Bx is added under CRC, so we see that it is added individually. So over here we can say that Ax and Bx are computed independently. Okay, so now coming to the CRC implementation by direct calculation, and when we are dividing x to the power 5 plus x to the power 4 plus x plus 1 by x square plus x plus 1, we get x as the remainder. So over here, the division of the polynomial using the modulo 2 arithmetic is a computationally intensive operation. So in the worst case, it requires a shift operation and an XOR logic operation for each bit of E. So as a consequence, this scheme is rarely used in actual systems. Okay, so now coming to the other circuit, over here we are seeing the parallelism of the CRC implementation is 1, and thus 1 bit is processed on every clock cycle. So multiple bits can be processed on every clock cycle to speed the CRC calculation. Over here we can see that the diagram is becoming complicated. CRC implementation by parallel processing, over here from the diagram we can see that the CRCs over here are treated as an individual block. So over there is less chance of interference, and the number of variables is m plus m minus 3. CRC implementation by serial processing, over here the number of variables is m plus p minus 2. So we can see that by serial processing they are individually, the code blocks is processed. So as we can see that the complexity kept on increasing, so we came to the Servate algorithm, which to some extent solved the problem. So over here the Servate processes an algorithm based on the lookup table. The Servate algorithm uses a single table of 256 32-bit elements and reads the bits bit by bit, byte by byte. Modern processors usually access 32 bits or 64 bits at a time. So as a consequence, the Servate algorithm is not as efficient. Some schemes have been processed in the literatures to solve this problem. Okay, so slicing by 4 and slicing by 8 algorithm. Kunavis and Berry proposed the slicing by 4 and slicing by 8 algorithms based on the lookup table. The slicing by 4 algorithm uses 4 tables of 256 32-bit elements and reads 32 bits at a time. The slicing by 8 algorithm uses 8 tables of 256 32 elements and reads 64 bits at a time. So the performance of the slicing by 4 and slicing by 8 algorithms is improved compared to the Servate algorithm. Okay, so coming to the conclusion. In 5G NR, the transport block consists of up to million bits and code block consists of up to 8448 bits. So due to the difference in the size of the transport block and the code block, the scheme of CRC processing suitable for the transport block and that suitable for the code block, both are different. Okay, this much from my side. Thank you.